Swayam Prabha. Digital India. Educated India.
Okay, so today's title is Advanced Manufacturing Technology for Biomedical Applications. I think this biomedical field is one of the very interesting fields which have come into existence recently, though there were such kind of an applications from several years, but these days, so there are several techniques which have come into existence, and then the medical, the way how things were done have been drastically changed. So biomedical manufacturing is also have developed a lot. So because the devices which are being used or need to be manufactured, and that too in a large scale. So even simple example, if you take, so even the injection. So earlier, actually, when we were children and all, we were so much afraid of injection. So even they used to have a joke telling that whenever we make something new sense, they'll say we are going to give you injection. So that means we are so much afraid. It's because the diameter of the needle was very large. So bigger the diameter, the more pain it will be. But nowadays, actually, the needle sizes are so small, so even you can't feel much pain. Just it will be like a small prick, and that's it. So thus the biomedical engineering and the biomedical field has transformed the way how things were done. Another example is that the pinhole surgeries. So earlier, if there is a surgery, so we need actually to go get admitted in the hospital. So then they will make the incision. That means they'll make the cut, and then after doing the surgery, they will stitch. And then you take so many days. You need to stay in the hospital. After that, the stitches used to be removed. So then you have the recovery phase and other things. But nowadays, with the help of a pinhole surgery, so they make a small incision. So insert all the devices which need to be going inside to do the particular surgery. Like for example, if it is a removing the kidney stones, so just you insert a tube with a small kind of a cutter, and then you'll have a suction pipe. So the whole device goes inside. So then when it has reached stone, means it is not like a stones, but it will be like a crystal. So the blades will open, then they'll be rotated. So they'll crush that hard material. So immediately we'll on the suction, and the blood and the fluids and also these hard particles will be removed. And after the surgery, the whole device will be retrieved, and then maybe just one stitch will be put. And also nowadays we have those materials which just get dissolved, and then you don't need to remove actually literally the stitches. So that is how the whole way how medical things were made have been transformed by this area. And also we see a very interesting kind of devices which have come up recently. So they are wearable devices. Now, generally, what happens is if somebody are a diabetic, so they take sometimes insulin injection or maybe a tablet. So then generally what happens is that once you take the insulin, the sugar levels come down, and then after that again it's keep increasing. So eat the food, it increases. So then you take the tablet, it decreases. So these kind of a cycle will be there. So instead of that, if you can have a device which can be like put to the skin with a micro and rather nano needles, so they'll be injecting the insulin at the regular intervals, so that the blood sugar levels can be constantly maintained without great fluctuations. And also nowadays, so if you want to monitor the blood sugars So even the heartbeats, rates, and everything. So we have devices, so which you can put like a patch. You can put it on your body, and then we have a facility actually to connect to our mobile phone, and you can get all the information. Okay, so these kind of devices have come and helping in monitoring and also even controlling so various aspects which are in our body. And also actually these devices can be remotely controlled. So if somebody doesn't take a tablet, or the sugar levels goes high, or the heartbeat goes high, so even the relatives or other people can be alerted, and immediately the action can be taken. So thus the biotechnology along with nanotechnology and MEMS, micro electromechanical devices, all these technologies have contributed to several medical devices which are helpful to improving our health and monitoring our health. So we also have the devices which are called as lab on a chip. So these devices, why they were called as a lab is that whenever we go to a lab, actually we conduct several tests. So it is not just a test, but several of them. So these microfluidic devices or lab on a chip devices will be of the size of small ID card like that, just an ID card size. Then there will be like different chambers will be there, and then in each of these chamber, so there will be chemicals or agents which will be required to carry out different tests. So for example, the blood can be put here, so it will flow into these chambers, and then different results, like if you want the sugar or other parameters, whichever you want to test, so they can give. And that is the reason these type of devices are called as the lab on a chip. Not just one test, but several of them can be calculated. And also probably we were not very familiar with these type of devices earlier, but during the COVID, so I think almost everyone would have seen and used these kind of a kits, so where you can get them by post, and then you can take the saliva or from the sample from the nose, and then put as they describe. Then finally the fluid actually flows in a micro channel, and then if the color changes, it is positive, or if it doesn't change, negative, like that they'll be, you can actually test. So these are all actually the lab on a chip devices, but sometimes they were made only for carrying out a specific test. Actually, even before all these devices were become popular, right in 2007, so we have actually machined a lab on a chip device by using our Kern machine tool, and also the micro machine tool which we have made. But at that time, I think not many appreciated it and were not knowing the use of it. But then later, so they become like household word. And even some more developments have happened, and it is not only just lab on a chip, but organ on a chip. So they call it as a OOC, organ on a chip has been developed. So what this function of this organ on a chip is that, for example, think that a kidney is not functioning. So we can actually make an artificial kidney. So for filtering, so all the characteristics what we have, the function what is done by a kidney can be done by using these microfluidic devices, and then that device can be put on the human body. So like it will be helping in the cleaning of the body and other functions. So you don't have to go for dialysis regularly, but this will be continuously working. So one of my student, Jennifer, so is actually working on that kind of a project. So where even we are trying to implement the artificial intelligence kind of techniques. So where we'll be able to detect, and also we'll be able to decide what is the kind of process and how much and how it should be able to behave. And also we have been trying to develop a device where we can even monitor various blood parameters. Now, as I said, when we were actually working on these kind of devices, I visited Deakin University in Australia. So there they were making a microfluidic device, which is actually required for separation of various particles, and they were using the injection molding process. So they have an injection molding machine. So even I was just looking at that, and then these kind of devices were made. So I brought some of them actually to India, and then we have put under our profilometers, and then when we looked at it, it was looking like this. So surprisingly, because it is an injection molding where you apply the force, though there are channels here, but when you apply the lot of force in injection molding, so they are forming some of these defects what are you seeing here. Then we thought, why not we try to make it by using our micro machine which is there. So when we machined it, so it is such a kind of a very clean cut, so where you can see the profile beautifully machined and without these kind of defects. But only thing is that in injection molding per minute you can produce a lot of these kind of devices, but in micro machining we had to machine them one by one. But other than that, if you look at the quality of the profile of these channels and also the other defects, so you get a very, very clean kind of devices. So with all these things, we got inspired actually to carry out the work in the biomedical field. So now when we also look from the angle of commerce or from the commercial angle, so we find that the global market for microfluidic devices is very, very high. So nowadays, I think they have calculated, actually we don't have the data in India in rupees, but actually it is available in US dollars. So where they say that it is $32.1 billion. And also they are estimating that, so it is going to increase even by maybe another 20 or more. So that will be $50 billion so per year. So that is the kind of growth which is there. And maybe even some of our students who have completed this work, Yugender is working in one of the biomedical areas, and another my student Pawan, so he was worked in a similar kind of thing, and now he has gone as a faculty. So thus there is always a lot of opportunities are there for these kind of manufacturing of these devices and also testing and related areas. So now with that motivation, so we started working on these devices which are called as the microfluidic devices. So what is microfluidics? It is nothing but the science and technology of the systems that process or manipulate small amounts of fluids. So the flow can be in the order of like 10 to the power of 9 liters per minute or even less. So that is the kind of order of the amount of fluids which will be using. And also the channels, so they are called as the micro channels, so of the orders of few micrometers. So the sizes can vary depending upon the application. And here we find few characteristics, something which are important and also interesting. See, now whenever we have these kind of a micro channels, when you put a drop of blood here, so they automatically actually it flows to the different areas. So in some cases, we have where we use a syringe pump and other devices, but most of the places, so you don't need even any energy actually to push. So because of the capillary action, so itself, it will be just moving. I think you'd have heard what is capillary action. So when you're studying about botany, trees, so when the sap actually just flows up from the roots to the branches, so it is because of the capillary action. That means whenever the diameters are very small, so the fluid actually flows even to a height. Okay, so or even if you keep it like horizontal, so it flows to different parts, and even vertical also it is possible. So thus these devices which are being used based on these kind of principles with a very small amount and then flow happening automatically, you have a lot of advantages. So saving of the energy, and the size is also small. And another important thing why these microfluidic devices are important is that so probably if you have visited the hospitals, or even if you have taken generally the elderly people to hospital, if you say we are sick, the first thing they will do is the doctor will prescribe some of the blood tests. So then you go to the lab, they take like syringes of blood. Already they are weak, and then they don't have blood probably enough quantity, but still they take out more amount of blood. So that is actually negative. But then if you have these microfluidic devices, the amount of blood which is required will be very, very small, few drops. So that would be sufficient. And the results what you get is the same as what you need. Okay. So thus microfluidic devices are very important, and they have several advantages. Then these applications actually can be used in several applications. So where you can actually make the devices to mix different particles or fluids. For the uniform mixing you can do, or for separation. So one of the examples what we have worked is the different cells in blood can be separated. So from the plasma which will be there, and the WBCs, white blood cells, red blood cells, so we can actually separate them. So even if you want to study the DNA structures, so they have particular devices. And then even in telemedicines and sensing, monitoring and controlling, in all these things actually we can use the microfluidic devices. But in our work, and specifically in today's presentation, so we'll be talking about how these devices can be used for separation. So microfluidic particle separation, there are several techniques which are there, which are, some of them are called active, and then some of them are combined techniques with passive and active, and other techniques are called as passive. So here what happens is that in passive, you don't need actually much of the energy from outside which need to be supplied. So in active methods, there will be a lot of amount of energy which will be required. So thus we have actually selected some of the methods. Only two methods we are basically focusing. One is called as inertia and inertial flow fraction, and other one is called DLD, deterministic lateral displacement. So there are other methods, so which will not be describing, but if you are really interested, we can give you information on other devices. So inertial focusing is one of very, very simple methods, so which have been used for separation of different particles. See, actually, when we are talking about all these technologies, you can actually observe them even in nature. So now, for example, if you go to a river, so then when the flow is happening and if the waters are clear, you can see that when the particles or stones are rolling, so the sizes of the particles, like which are small, so they all will come to a particular distance, but the bigger ones flow only to a particular distance. So there will be a kind of segregation which will be happening. So even that is one of the principle. But here, the principle what we are focusing is that, so when the flow is happening in the micro channels here, so these particles actually, because of the inertia toward the wall, so they all segregate towards the wall. So initially, so the particles will be actually like this randomly distributed, but after it flows to a particular distance, then we find that they are all actually focusing towards the walls. So then we can have a mechanism, so by means of which we can separate those particles. Then the second method on which we were concentrating is called deterministic lateral displacement. So in this, what we do is the specific arrangement of the pillars. So rather than a post, we can call it as a pillars. So they precisely control the trajectory of the particles, and then the resultant of it is the separation of the particles. So like a large and a small, so they actually get separated. Yesterday, I think we have been talking about texturing. So in that, one of the application is the microfluidic devices. So yesterday I didn't show them because I wanted to show that one. So here what happens is, if you have a channel, so think that this is the micro channel. So in this one, if you can make a micro or rather nano pillars, so then you make the fluid actually to flow through that. So the particles which are small, which are large, actually they'll come here, they hit this, then they jump, then again they go like this, then go. And because of that, they start moving in a separate direction. And if they're small, so they go through the zigzag path in between these pillars, and then they move and they get separated. So this is actually a very interesting phenomena. So there again, yesterday, as I said, whenever you want to make the texturing, the dimples, so we need to know what should be the size of the dimple. So what should be the distance between each of these dimples, and that we call it as a pitch. And then if you have 2-3 rows of them, so what should be the distance between them. So all these parameters we need to decide. And similarly, even when you are making these micro pillars here, so we need to look at what purpose it is being used, what is the type of particles we are separating, and then based on that, we need to decide the size of the pillars, the distance between the pillars, and also if you have a different rows, so how distance you need to place them. So all these things actually plays an important role. So now, first we are going to look at the microfluidic devices with inertial flow. So for this, we need actually the channels. So where you can have a input here, and then you can make it to flow into the channel, and then later you can actually have two separate things based on what are the kind of particles what you're going to separate. But now the problem is that, so in many cases, for us to separate these particles, so this much length is not sufficient. So we need long length. Okay. Then how do we achieve that? So if you have straight line like this, so probably you need to have 1 meter length of a device. No, we can't do that. So we are talking about the size of these devices. So something like an ID card size or even smaller than that. So for achieving that, so what we are going to do is that we are going to place these channels in a different fashion. So there are different ways how we can do that. So here for our work, so we have selected the serpentine channels. So thus you make these serpentine channels so that even just in a particular length, you can have the flow for a longer distance. Now, when I make a serpentine channel like this, how can we make it? So you can have actually a curvature here, or you can also have a square kind of a thing, or even we can make these kind of a channel. So there are different ways which is possible. So we have actually tried all these things. So then to see which one will be more effective in separation. So probably if you have like this, so when the flow is flowing like this, suddenly it need to change the direction and then go. So it will be like that. But here it will be more smoother. So all these characteristics we need to capture to see what would be the best way how we can separate. So generally at the end of these things, so we can have like what you want to separate. So along the walls it will be one. So toward the center it will be different particles. So like plasma comes here and the WBCs or RBCs will be coming here. So thus we can separate them. Now to study all these characteristics, so we have actually carried out the simulation of the flow, what is going to happen. So these were actually designed in the CFD, computational fluid dynamics, and then there will be several parameters which need to be described. So what will be the flow rate, what is the diameter of these particles, so then what should be the velocity of the flow, the channel width, and also actually even the channel geometry, whether it is like this or like this, and even the surface finish. So how the bottom of the channel is there, how these side walls are there. So sometimes when you manufacture these kind of a channels, so we can't actually get straight like this, but sometimes so they'll have a shape something like this. So if you can get a vertical cross section, that will be good, but doesn't happen. So sometimes these gets curved. So like this, and the surface roughness here at the bottom and even the side walls, they also affect the flow. So all these things actually need to be considered, and then those parameters need to be given so that we'll be able to understand what exactly will be happening. So thus we tried with different cross sections and flows, and then we found that whenever we have this kind of a section, there'll be a particular kind of a path where these particles will take. So like for example the RBC, so then in that particular path you can have a cross section and you'll be able to separate these particles. So these particles are also we look what is called as a streak lines. So those curved lines are formed by a string of fluid particles which are passing through a certain point, and then we can study them and we can see how the separation will be happening. So if you have generally for us like 20 micrometer particles at 0.3 ml per minute, as I said, the flow rates will be very small. So in this cross section, we were able to get a good one, and also 20 with 0.7 ml per minute. So they were giving the good results. So like that, we have studied. Now, theoretically, we did study. It looks fine, but how do you fabricate them? So that is another big challenge. So now, before going into that, I would just like to see if you have any questions. Do you have any questions?
Sir, can you please brief about about the serpentine channels?
Brief means what are the details you're looking for?
So, could you please provide more details about what is serpentine channel? Or is there any other designs adopted? You said about that zigzag design, that curvature, square, and triangular. Any other particular design?
Okay, so these kind of a devices. Okay, actually, if you look at them, these are one of the simple kind of a designs. So we have even actually later, I think we have not put those thing here. So wherein you can have kind of a free-form kind of surface, it's like an eel kind of a shape, and then you can have even different cross sections. Okay, so here it can get narrowed or increased or small. So and then you can have any kind of a free-form surface. So free-form kind of a curve, and with varying cross sections. So where you can manipulate the flow. So there is no limit for the geometry of these channels. So probably maybe after the lecture you can go and look at microfluidic devices and then their shapes. So you have n number of designs with whatever geometry you think you'll be able to use them. So here one of the examples like eel. So Jeshurin and even Selva Kumar who are there. So they have designed, and then we tried actually manufacturing them as a part of our micro manufacturing course. They have presented. I don't know if I'll be able to pick that and then show. Otherwise, when you visit the characterization lab, so you can ask for that and then look for it. So thus you can have several kind of a designs for the cross section and also the geometry.
Thank you, sir.
So now, yeah, is there any other question? Or we can go ahead. So now, making these devices is the challenge, because the micro channel itself, we have said it is few micrometers, and then for DLD method, we need to put the sub-micro or nanometer kind of a pillars at the bottom. So that is the big challenge. There are several methods which are there and which we have tried. So photolithography, I think you should be familiar with that. That means we'll have a mask. So then we'll have a substrate. So then we put the UV light. So wherever mask is there, that material remains. So other thing will be removed. And thus we can make the channels which are required. Then hot embossing. So we can actually emboss them like the embossing what we do in metals. So similar to that in these materials. So PPMA, so where we'll be able to hot emboss and get the shape of these micro channels. So usually we use a heated wire, then put them into the required shape, and then we'll be able to get the shape. Then 3D printing is another technique. So actually we have tried this method. I have visited the University of Technology, Sydney. So where we tried printing these devices by using the 3D printing, but we had few challenges. So the problem is that if you print the whole device in one go, so then we have a difficulty. Like inside the cross section of these micro channels is very, very small. But in some places, the 3D printing, actually they were getting blocked. So even in one place, if it gets blocked, the whole device doesn't work. So we tried actually pumping high pressure fluid into that, but there were several blocks there. So then later what we started doing is that we don't print the full device at once. So that means you can have micro holes and the channels inside. This is a cross section throughout. But instead of that, so what we can do is that you print half of it. Okay. Oh, sorry. So we can print half of it in one, Then the other one either can be straight plate or it can also have this. So what I'm trying to tell is that if we need, sorry, I'm drawing with hand. So this is one part, then another part, this is the cross section. You can actually, sorry, I'm writing over this thing. So they can be like this, you can have, and then we can print these devices. So, but then when we tried like this, the problem was aligning them properly. It was difficult. So sometimes what happens is if you don't align, so they become like this, then we don't get the proper flow. The other method is that you print a micro channel like this and then put a flat, just a plain one like this plate over that, and then we can use these devices. Okay, so that is another way how we can do it. So we had actually very difficult if you have to make the whole device in 3D printing. Then we also have etching, and finally we use the laser, so where we could actually get a beautiful profiles. And other advantage with the laser micro machining is that we can actually make the masters by using the laser micro machining on the metals, and then we can also actually get the replica of them and produce several these kind of devices. And we also actually tried the mechanical micro machining, so whereby using the micro milling, so we were able to achieve them. So I'll give you a few quick details about how we'll be able to do that. So some of these devices actually we have developed at in-house in our IIT Madras, and some of them we have done it at MCN. So it is called Melbourne Center for Nanotechnology. So where our students actually, Jeshurin has gone there, Pawan and Yugender also visited, and now Jennifer also will be going after a few days. So there are facilities for lithography, making these silicon masters, and then we can make the replica of them. So this is an hot embossing method. Then we have photolithography, so wherein we can get a very accurate shapes. So these are some of the devices like what we can make. So it need not be serpentine, so it can be different shapes and sizes. So then we can produce them. So there are different steps which you need to follow. So lithography is something, lithography means like writing, where you have a photopolymers and then UV light will be used, and then we can produce these components. And similarly, the ion etching, so we can have the ion etching process, so deep reactive ion etching. So again, various sections, parameters and sizes can be produced. So these were all the devices which we have made with different techniques. So the PDMS is the material, so deep reactive ion etching, embossing, micro milling, so 3D printing, then photolithography, and then this is again deep ion etching with a different shapes. So then once we do that, we can replicate them and then make it on the PDMS particles. So now the big challenge is that we need to make those pillars. Okay, sorry, we have kept all the things in one slide. So how do we make these pillars? What should be the size of them, and what should be the cross section? Is it circular is good, or triangular shape is good, or what is the best one? So again, actually the simulation helped us in finding out which is the best cross section, and then we have decided only two of them, like this kind of an section, triangular you can call it, and then the circular section. So micro milling is another method. So as you said, we use the Kern machine tool and the miniaturized machine tool setup which is there in our lab for doing these things. So these are details about the femtosecond laser. So we had a lot of difficulty there. So we can use actually the energy of up to 40 microjoules. As I said in the previous class, so 40 microjoules looks to be small, but when it is given at 10 to the power of minus 15 seconds, so it is very, very powerful for melting even the metals. So using that we have done, but if you don't optimize them and then move properly, so we couldn't actually initially get very good profiles, but later actually we have worked on it, and then with the optimization, so we're able to get a better kind of profiles. So once we have these devices made, so we had initially made the designs, so then analyzed with the CFD and tried to get what is the best profiles, and then finally the experiments. So for conducting these experiments and observing them, so really it is a challenge. So what we have done is that you would have heard about what is called as a syringe pump. So where it will be like a syringe where we can press them. Then that is done actually with the motorized one. So you can see it here, and also later in another picture I'll show you what is this syringe pump. Now through that, so we are actually going to pump the blood. So and it needs to be diluted. So it will be diluted and then pumped through this device. Then later we can actually separate the plasma and RBCs. But now it looks fine, but these particles are small and we can't actually see them with our naked eye. So for that, what we have done is we actually mounted it on a microscope under this. So we had, it's not as simple as that. So you make a device, then we need to connect these tubes, but it has always been a big challenge. So you have a microfluidic device, which is something like this flat. So then you'd have seen in the device, the holes like this. So input, maybe input you may have only one, and then output, say that you have 2 or 3. So up to this it is fine, but how do we make the fluid to flow? So you can see here these tubes. So what you are seeing here, and also the tubes here. Now, how do we connect them? So we had a lot of challenges in connecting them, but finally with kind of a glues and other help, we are able to bond them properly, but some devices still were leaking, but later we were able to achieve that with a precise bonding techniques. So these need to be connected, then pump the fluid through this. So it will go through these holes, and then we can have different devices, and then the separation will be taking place. So that can be collected here, and that can be visualized under the microscope. Yeah, actually we had the videos of it, but I think here we have put a static pictures, so where you can see that how the blood particles are getting separated. So you can also observe the bonding which has been made so that these devices will not leak. So this will be the input, and then output you can see one is plasma where there is no color means. So the RBCs are separated into this. The other 2 chambers, it is plasma. This is the syringe pump, and we can also actually observe that in the computer when it is microscope is integrated. I would have wished we could have had the videos of them, but here we have the picture, so you can see that because of inertia, so these particles getting separated towards the wall, but then in the center you see the clear fluid. And one more technique actually to visualize these things more clearly is a more advanced kind of a method. So that is called as flow cytometer. So this is called flow cytometry. So it can be used to determine the particle efficiency by analyzing the light which will get scattered and then the fluorescent signals. So what we generally do is that we need to put these devices in the flow cytometer. So it is actually there in biotechnology department in IIT Madras. So when you make the sample to flow, so then these particles actually will be made to flow through a small microchannel, and then you put the laser light, so then it gets scattered. So depending on the size of the particles and then what particles they are, the fluorescence actually changes, and then the flow can be visualized. So how these particles are moving and what are the paths of each of these, that is called as a streak lines. So of each of these particles can be visualized much better if you have the flow cytometry. So after making all these things, actually we found some of the parameters, so which were able to separate the blood more efficiently. So probably if you are doing the research, so that may be of interest. So where the flow rate of 0.3 ml per minute and with the 1:100 dilution, so we're able to achieve a good efficiency. And similarly, with the different particles and square form, so we could find that for each of the channel, it was a different parameters which was giving the best for separation, more efficiency. And also, as we have said yesterday, so we have actually used the goniometer to find out the contact angles and also to test the surface. So as I mentioned earlier, there are several parameters actually which will affect the flow. So one of them is the nature of the surface. So thus, if the contact angle is below 90 degrees or above 90 degrees, so we find that the flow characteristics changes, and then based on that we can decide what will be the best method. So we generally observe that when we have 3D printed and we used two different liquids, so one is water and other one diiodomethane. So what happens is that when we 3D printed these surfaces, the angle what we obtained is like less than 90 degrees. With micromilling it was different. So with photolithography it was more than 90 degrees. Hot embossing it was less than 90 degrees. So thus each method of fabrication actually gave different characteristics of the surface. And then with that, when we conducted the experiments, so we have found that hot embossing was giving one good results, and then with micro milling, so we had good results. So like that, with the different types of materials, so it was giving a different characteristics. So we need to still standardize these methods and the way how we manufacture them. So in a mass scale, so all these things need to be calculated. Yeah. So any questions here? Okay. So if you don't have any questions, I think we'll go. Yeah, sorry.
Good
Yeah,
morning, sir.
please. Yeah.
I have a question from Pepto2. I want to know in what way can be improved the Pepto2 for large area?
Femtosecond.
For large area, that process,
Yeah.
how can improve in the large area?
Yeah. So as we have been telling that femtosecond laser is a very fine machining method. And here large area doesn't come into picture because the devices are very, very small. So the size of the microchannels and even the pillars what we make will be small. So thus it is not the large area, but the question would be how do you produce them in mass, like mass production? So that becomes the challenge. So for that, what we can make is we can make the dies. We call them as a masters, and then we can reproduce them on the PDMS or PMMA kind of a material. So is that your question or it was different?
No, it's okay, sir. And I have seen some photolithography. We are using some material. So which material will be suitable for this? For
Yeah, so you
fabrication.
mean photo mask, or you mean the material which is used as a substrate, is it?
Yeah, for molding.
Yeah, so the
fabrication.
substrate we have different types of materials, but only important thing is that they should be sensitive to the light. So when the light falls on them, so they should actually, so in some cases it will get actually solidified. So it is photoelastomers kind of a material where they are sensitive to the light. So what we do is, I think this lithography means it is called writing. So wherever the light falls, the curing actually takes place. So, and then that becomes a solid. Other part remains like a liquid. So any photopolymer, we call them, which is sensitive to light, and here it will be UV light, so that we can use it.
Yeah, thank you, sir.
Okay.
Good morning, sir. So my question is that before flow cytometer, you were explaining about an experiment where you use blood sample to determine its path lane. I just don't understand what is the mechanism behind it. Like, what is the basic idea of it?
Oh yeah. So actually, no. So here also actually we can study. So even flow cytometry gives a better picture, but the facilities are not that freely available. So what we have done is the same devices, we have kept it under the microscope, which is there right in our lab, and then we tried to visualize the flow. So we have actually videos, but I don't have right now put it on the PPT. And what basically has happened is from one side, we dilute the blood. Actually, we tried with different blood. So we use the goat blood and also the human samples, but we have what is called as an ethical committee. So if you are using these kind of blood, especially the human blood, we need to get the even animal blood, we need to get the clearance from it's called as an ethical committee. So we don't want to harm either the animals or human beings, and also we need to take care of the safety. For example, if that blood is contaminated and then while handling it, if it pricks you and then gets into you, then you may get a disease, or all these kind of risks are there. So there on that experiment, what we have done is that we took the blood samples, so then diluted it on from one side. So we send the blood. So we have the microfluidic device inside, like this micro channel. So the designs what we have shown. So then here, I think in the design, if you see, there are 3 chambers. So after, we maybe serpentine channels I can show like this. After that, they get actually 3 chambers here, 3 holes. So where and each of them there are two white one what you are seeing. So these are actually this one and then this one. So where the plasma is coming out and RBCs are coming in this. So that is the reason you see that red in color. So only one channel you see here, it is red in color and other two are white. That means the plasma in the blood, if you remove the RBCs, it doesn't have a color. So thus these two channels, it is white and the red one is the RBCs. So thus, if you want to separate the RBCs from the plasma, so this is the method. So that is the experiment what you have done. Is
Yes,
it
sir.
clear?
Yes, sir. Thank you, sir.
Sir, good morning, sir. Can
Yeah.
you explain more about the inertial focusing, sir? You said the particles move to a defined position. How do they move, sir? Like the principle behind?
Yeah. So now I think we just go back to the principle here. So here what is going to happen is in the flow, when you see like this, when you put a wall here and then make these to flow, they actually get moved. The particles will be moving like this. And also here, if you see, there'll be a shear gradient, so which will lift these particles. And also actually this kind of a phenomena you can see even in a channel. Okay. So now when the flow is happening, you find that these particles actually are attracted towards the walls because of the inertia. So here the particles will be touching the wall and then their flow characteristics become slower and then these particles will come towards the wall and in the middle it will be clear. So these kind of things you can even observe in your day-to-day life. So when maybe in a channel, open channel also, when a river or a channel is there, you see that whatever the dust particles or something is there, they come to the wall. Have you observed it? And center one will be clearly, it will be flowing. Have you observed this kind of a phenomena?
Yes, sir.
Yeah. So because of the inertia, so these particles actually comes like that. So based on the size and all during the flow, they get attracted or pushed towards the wall. So because of the shear gradient which will be there during the flow.
Yes, sir. Thank you, sir.
Sir, while mentioning about different fabrication techniques, you said about 3D printing, no, sir?
Yeah.
Sir, could you please provide me some more details about this particular technique? You said it will be printed half and half, and how can it be aligned accordingly?
Yeah, that is the challenge we had. See, first attempt, what we have done is in Australia, so we have printed the whole device as one. But then we had the challenge, difficulty of some of the channels get blocked because it's a kind of a powder and then a layer by layer when you are printing. So some of these things get stuck. So that is obvious. So what I was trying to tell you is that instead of how do I show the cross section? If I take a cross section, instead of printing it like a whole piece like this. So here what happens is when I'm printing, so this bottom face, so it will print like this. So when it comes to the hole in this layer, it will print like this. So then there will be a gap, so smaller gap, then it will print. So then this one slightly bigger gap and then it will print. So then it prints like this and like this layer by layer it will be going. So then later when you try to come like this and when you are printing, so it should theoretically it should come like this and then this one will be straight. So I'm not able to draw it clearly, but I think you are able to see this, no? Okay. So this is the whole section. But the problem is that when you are printing a layer like this here, some of these molten material so comes into here, and then it blocks the microchannel. Even if it is blocked at one place, we will not be able to pump it. So for that, what I am telling is that, so we can print half of the channel like this. Okay. So then print another half with the shape, and then later put them together. But this one, the big challenge is that it is not one section, no. So when you are trying to put it, they don't sit properly. And usually we use the glues and all. So once you put them, it gets stuck and then we cannot align it. So that is a challenge. So what I am suggesting and what we have tried is that just print a channel, that's it, like this. And then take a flat plate, which is not machined, nothing. Then close it. Okay. So put the adhesive and close. So there you don't need any alignment. So just take the two plates and then so the PDM and devices, and then close them. So this becomes the chamber and the flow can be achieved. Is it clear?
Yes, sir. Thank you.
Yeah, so Pawan also joined, I think. Yeah, so this is the DLD device. It's called deterministic lateral displacement. So this already we have mentioned. So when you have different particle sizes, so either they bump or they pass through them, and because of that, the characteristics changes, and then we find that the separation will be taking place. So thus we have actually carried out the simulation with the different cross sections, and then how these flow characteristics will be there, and how particles get separated, what should be the best geometry of these pillars, whatever we make. Is it circular, or it should be different sections? So we find that when you have a section like this, it will be a smoother flow. If there is any problem with the cross section, they get separated, and all these things we have tried. And also we tried with the triangular one. And then if the flow is in this direction, so they also change the characteristics of the flow. So different combinations we have tried and then manufactured this, and we have studied. So different names were given with the sizes of these triangles and their characteristics. So there we find that with a particular characteristic, so both the first and the third outlets have a kind of thing, and this is the efficiency. So based on which what is the most efficient one, we can actually use that. So these are different flow characteristics what we have obtained, and then finally after we fabricated them and then used, so this is the way how the flow was getting separated. So on the left side is the simulation, and on the right side you can see the actual particles being separated. So there are more of the details of it. So there was a problem with this adhesion. So we tried testing them, subjecting it to tensile strength, and to see whether these devices are going to peel off or not. And this is the syringe pump which you have used, and then the counting also has been done. So how many particles we are able to collect, how many cells we are able to separate with the different ratios and with different size of these pillars and shape of these geometries. So these are some of the things what already we have explained, but these one with the DLD kind of devices. Yeah. So these are some of the things what we were able to achieve through that. So we'd like to thank all the people. I think I'm mentioning about our students who have completed their PhDs. So Yugandhar, Pawan, now they're doctor. And Professor Ling Su Kong from the Deakin University. So he has been collaborating with us, and we visited there, and we've been carrying out the work. And this is from UTS, University of Technology, Sydney. And the MCN is a very good facility. So where you can do all the lithography, the masters on silicon, and also all these things are there. So if you want, you can type this name and you can look at the facilities which are there. Thank you. Yeah, we have short time for. Yeah, Pawan, you'd like to share your experience?
Actually, like you have already explained all the things. So mostly yeah, so the experience at MCN was a good experience because they had a lot of equipment with them and like fabrication techniques. Is that like it started from micro fabrication to nano fabrication, and we also had a facility for PDMS labs. So that is what gave us an experience of building it in IIT Madras as well. So yeah, thank you for all the opportunity, and yeah, it was a good presentation. Thank you.
Thank you. Yeah, any other questions?
Good morning, sir.
Yeah.
My question is regarding to finishing of internal surface of the microchannel. How
Internal?
this? My question is like how the internal surface of the microchannel affect the performance of the micro of this device, like if I can say like this device, like the surface of the internal channel is like soft or roughness, how this affect the result or the output of this device?
Yeah. So actually, we started looking at that into detail, but it was a bit challenging. See, now what happens is that, as I said, when you machine with the different technologies, so this is the micro channel, each kind of a method has its own characteristics. And now, if you want to change that and achieve something better, it becomes difficult. Like, for example, when we machined by using the milling cutter, so you know the milling cutter with a flat face milling kind of a cutter, we could get a very, very good surface finish here. So usually the surface finish will be like this. So now when we magnify it, okay, so the bottom, though it may look smooth, but actually when you magnify it, it will be like this. But controlling that was a big challenge, and it also depends on the process which we are going to use for manufacturing. Like if I use a 3D printing, so usually the surface will be rough, and probably we may have to again do another processing, maybe one milling we may have to do to get it good surface finish. So thus the surface what we generate depends on the method which we are going to use for fabrication. And if you are using the masters and then we are replicating these devices, again the accuracy and surface finish of the master itself plays an important role. Now, if I understand your question, when we have this kind of surface finish, how it affects the flow? Is that your second question?
Yes, this is my question.
Yeah. See, now, for example, if it have had theoretically something like this kind of a surface, so when I have a flow, it would have been very nice. But now when I have these kind of a surfaces, as I said yesterday, generally, when we are going to manufacture these surfaces with all the methods, what we have told, it will be a stochastic surface. So that means stochastic means it is a random kind of a profile which will be looking like this. But now in our DLD, what we have done is that we have wantedly put those pillars which are very systematic one. Okay, so this is a kind of a texturing or making these pillars and then studying it. Now, if you have had this kind of a surface, theoretically it will be fine. If you have like this, so the flow gets affected. And if you have a systematic pillars like this, the flow characteristics will be different, but we are utilizing that for separation. So thus obviously when you have different surface, so it affects. And also we have told you about the contact angle. So why we try to look at that is that surface nature is important, whether it is hydrophobic or hydrophilic or how it is going to behave. So if it is wetting the surface, the flow will be different. If it is non-wetting, so then the flow will be different. So thus all these parameters actually affect the performance of the flow patterns.
Sir, in case of especially in car engine, like to finish the internal surface of the parts, we are using abrasive flow jet machine. Can we develop something like that to achieve this surface?
Yeah. So we have actually thought of and tried to attempt. So what happens is now we have a micro channel. So before testing them or using it for our test, we can make an abrasive fluid to flow through this so that all these irregularities, whatever are there in the walls, can be smoothened. So that is actually possible. So we can try those things. So make the micro channel, then make an abrasive particle. So we need to particularly select what should be the size of the abrasive particles, because these channel sizes can be 300 to 500 micrometers or even smaller. So thus the size of the particles should be properly decided, and you make it to flow through that. So it will smoothen the surfaces. And some challenges will be sometimes these abrasive particles can get struck, or what you call it as an impregnated. So they can get impregnated to the walls, but you need to take care of it. So even in some of the devices which are used for medical purposes, so we need to be little careful. So it should not contaminate it. If they get stuck or impregnated to the wall, so it may again cause other obstructions for the flow. Yeah.
Thank you, sir.
Thank you. Okay. Yeah, if you don't have any questions, Chittaranjan, any question is there? Or? Okay. Okay, fine. Yeah, if you don't have any questions, we'll stop here. Thank you very much for your attention and your active participation. So as we said, we need to thank several people who have been working. So our students have been like our hands and legs for us. And there is a cooperation from different departments. So applied mechanics department, biotechnology department, then our mechanical department. So on different universities. So with the help of all these cooperation and help from them, we are able to carry out this type of work. Thank you. And also now we have collaboration with CMC Vellore, so the medical doctors, so that we can get the real time or the practical information from them. And also we have collaboration with Sri Chitra Tirunal in Trivandrum, so another university. So our students are, we are collaborating, and they are jointly guided by faculty and the doctors. They are basically doctors and also faculty in these colleges. So they have been helping us in carrying out all this work. So we thank them all. Yeah, we acknowledge them. Thank you.